we always talk about scattering cross-sections. But many of you do not know what cross-section is. You do a lot of calculation with radar cross-section, you don't know what it means. And then there's antenna cross-section, antenna aperture. A lot of you work with antennas, but you don't know what antenna aperture means. Okay, and then there's this very important optical theorem that few students know. And it's hardly taught in any courses, but I think you can read it up in Jackson. And it makes a lot of sense. I guess that was the first problem. The second problem, what was it on? Second problem was on density of states, right? Local density of states and that kind of thing. Spectral Green function, proving of the self-Hermitian property. Those you can draw results from chapter 5, and then you prove why the spectral Green function is a Hermitian operator. And you can go about proving those things, and then there's a complicated derivation of an integral, where originally it was a summation. You convert it to an integral, and you can find closed form integration. Okay, I think it was the second problem. The third problem was on chapter 9 of my book, which I hopefully will touch on today, on the radon transform, slice projection theorem, and that kind of thing. The fourth problem is on surface plasmonics. Okay. So if you find any error with the take-home exam, let me know. I'll fix them. Okay. So we've been talking about surface plasmonics, an interesting area, and then we have been talking about nanoparticles. Nanoparticles and why nanoparticles shine in prelims when you make them into small particles or small particles. Okay? So let's maybe continue with nanoparticle and then we'll continue. Chapter 9. But are there any special topics that you'd like me to lecture on in this course before we end? Because after Thanksgiving, we only have 2 weeks left, and only 3 lectures. What? 4 lectures? The second week, I think the Wednesday is the last day of class. So the second week, I only have Monday to lecture. So we only have 3 lectures after Thanksgiving. So if you have any special topics that you'd like me to lecture on, let me know. I can talk more about nano-optics if you want to, more from Whitney's book. And okay, so we talked about nanoparticles and how you can actually find the polarizability of a nanoparticle quite easily. And you can assume that if you have a nanoparticle, a spherical one, epsilon 1, epsilon 2, you can easily solve this very simple boundary value problem. This is 1, this is 2. If dz is p r cosine theta, and then phi 2 is equal to minus e0 r cosine theta plus a over r squared. A cubed cosine theta. We can match boundary condition, tangential field, E field is continuous, normal D is continuous, or you can also say it differently. Tangential E continuous is the same as saying that the potential has to be continuous. Because gradient of the potential gives you the electric field. So if this is continuous, tangential E will be continuous. And then the other boundary condition gives you normal D, and then you can find your A and B. And I found A and B to be equal to that. Two epsilon 2 E naught, and then B would be equal to minus 3 epsilon 2 over epsilon 1 plus 2 epsilon 2 E naught. The key thing to remember is that for plasmonic nanoparticles, this thing can go to 0. And when this thing goes to 0, then this particle is actually resonating, and they show the brilliance of color when you shine light. Okay. So far so good. Are there any questions? I asked you to think about ways on how you can change the resonance frequencies of these particles when they're that small. So you can figure out ways where you can change the resonance frequencies. Okay. Let's talk about the far field generated by these nanoparticles and how they look like. Okay. And this is the near field. This is the near field. So in a near field regime, A is much less than lambda. A is much less than lambda. Hence you can just forget about the electrodynamic effect. Okay, so any equation that is wave-like become Laplacian-like. Okay, but you can solve this electrostatic problem near field. So how do we get the far field out? Another thing is that I'd like you to be able to argue yourself is that you have Helmholtz wave equation. In this manner, when you solve an electrodynamic problem, but then for electrostatic problem, you need only to solve this problem. How can you argue that this equation becomes that equation in the near field? I think Aditya, I told you this before. How do you argue that the first equation becomes the second equation? When the frequency is low and close to the particle?
And frequency is low, k square is almost 0.
Say if I do not change my frequency, I keep my frequency at 400 nanometer, so k is always very large. Say I operate in optical frequencies. How can I argue that I can drop k squared with respect to the Laplacian square?
You're close to the source and you're closer to the singularity of the Laplacian dominant.
That's right. When you're close to the particle, the field has to change like that, and then the potential has to change like that in order to match boundary condition, which means that the potential has to change on the length scale of A. This is 2A. Okay. So the potential has to change in this length scale in order to match the boundary condition, which means that this Laplacian must be changing rapidly. If we do dimensional analysis, it has to change at this length scale. So this first term has to be proportional to this around the nanoparticle. Okay? Because it's proportional to that, then when you compare this term to that term, you're comparing 1 over A squared plus K squared. Phi, roughly. Okay, these are dimensional analysis, they're all rough concepts. So you have the fact that K squared, A squared is much less than 1. Then this would become just 1 over A squared. Phi is 0, or it becomes Laplacian square phi equals to 0. Okay? That's what the fluid people do all the time. They do dimensional analysis to figure out what term is important, what term is not important. There's something called the boundary layer near the fluid surface. And near the boundary layer, if you have any hard surface, if any fluid is to flow near the hard surface, due to the fact that particle has 0 velocity, they have to stick to this surface. The particle velocity is 0, but then away from the surface, the particle velocity is not 0. So there's a boundary layer like an exponential decay away from the surface. Okay? And in that boundary layer, the fluid velocity changes rapidly. Because the fluid velocity changes rapidly, viscosity becomes very important in fluid. Because of that, the boundary layer actually determines the dissipation in the liquid if you have a viscous fluid.
Where is
And
the
it
boundary
goes-
layer?
what? Boundary layer is this thin layer of rapid velocity change near the surface, in a fluid flow, in a hot surface. That is called a boundary layer. You might come across it before. Okay, a boundary layer. And in that boundary layer, the physics is quite different. Inside the layer compared to outside the layer. Inside the layer, velocity changes rapidly, so viscosity becomes a very important factor. And you cannot ignore viscosity inside this layer. And outside, you can ignore viscosity most of the time, but not near the boundary layer. That's what happens in fluid physics. Anyhow, so we have this near field solution. How do we get the far field solution from the near field solution? Well, we can do something clever. We can use the concept of Rayleigh scattering. How many of you know about Rayleigh scattering? Okay, 1 person, 2 person. Okay, most of you, 3 person. Most of you do not know what Rayleigh scattering is, right? Can I assume that? Chris, do you know? No? Okay, let's talk about Rayleigh scattering. Rayleigh scattering is the scattering solution by small particles that Lord Rayleigh did maybe around the turn of the century, early 1900s. Okay, so he assumed that if you know how to solve this small particle problem, if you're close to the particle, you know how to solve for its dipole moment when you have an electric field in its presence. And then the second contribution here is essentially the dipole field. Okay, so the dipole field is proportional to A over R squared A cubed cosine of theta. And the next thing I need to do is to relate A to the dipole moment. And I can do that quite easily because I know that the phi due to a monopole, is equal to Q over 4 pi epsilon naught R, right? That is the Q due to a monopole. And that comes from solving Laplace's equation due to a point source. Is equal to minus Q over epsilon naught delta R. So if I have a point source, I solve it, I got a point source Green's function, and that is the solution due to a monopole. Okay? And then if I have a dipole, it essentially is due to 2 point sources. Place a distance L apart. If I put the plus charge and the minus charge next to each other, they become dipoles. So the idea is that if I put this monopole solution next to each other, and then if I write down the dipole solution, it should be equal to Q over 4 pi epsilon naught R, and 2R, okay, one is R plus Z delta L over 2. I just displace it in the Z direction, and let's call this the Z direction. And then minus 1 over R minus Z hat delta L over 2. So these are two monopole solutions superposed on top of each other. Okay, you can do a Taylor series expansion. This is just equal to R into 1 plus how do I do this? I can actually do this in a number of ways. I can also write this as a, I guess I can write this in a very complicated form. X squared plus y squared plus Z plus delta L over 2 squared. And then take the series, Taylor series expansion of this. And I can also do other tricks like R plus Z delta L over 2 magnitude squared is equal to R plus Z delta L over 2 squared dot at each other. Okay, R plus Z delta L over 2, and then you have R squared plus Z dot R delta L plus higher order term. Okay, you can just Taylor series expansion that, and then you can take square root of this now. Take the square root of that. It must be equal to R 1 minus 1 plus half.
You'll need to rearm it first.
1 plus half
So it'd be the code
Z dot R delta L, right? If I take square root of that, they're doing right. There must be an R over. If I take square root of that, I get that number over there. Okay? So if I take this expansion, they get that. If I take the other expansion, they get the other term. I get something with a negative sign here. Delta L.
There's no half.
No half. If I
No, it
take
takes
it
square
out,
root to get half, right?
half, you get a square root from half, right?
Oh, okay.
A
Delta
plus
L over 2, okay.
1 plus
Sorry,
x
sorry.
to the half is 1 plus half x. That's where the half comes from. So now if I take the reciprocal and subtract the 2, I get the dipole solution. I get the dipole solution, then I get phi dipole must be equal to q over 4 pi epsilon naught r squared. It is common to both. Just as r squared, and then these two terms will cancel each other when you take the reciprocal and subtract, and what is left is only the first term. Okay, the first term gives me something like 1 over r. 1 over r squared, right? 1 over r squared, then c dot r x delta L. And then when I subtract the 2 becomes 1. So I get something like that. Right? If I take this reciprocal and subtract, and then the half becomes 1, because I have 2 of them, I have this as my solution. And z dot r, if I take this my r hat, my z hat, z dot r is equal to cosine theta. So my q dipole is equal to q delta L over 4 pi epsilon naught r squared cosine theta. That is my dipole here. Am I right? Did I get that right? I seem to be missing a factor of 2 small.
Oh, actually, I have a question.
Yes?
In the denominator, you have just an r squared, but when you like, in the denominator, those two terms will be multiplied, right? So you'll have like r squared minus 1 by 4 into something else.
Let me see if I take the reciprocal of this, what do I get? Let me see if I get things dimensionally correct. This is dimensionless, this is dimensionless, this whole thing is a dimensional length. So if I take the reciprocal of this, let me take the reciprocal of this over here. It should be just a reciprocal of first term, and then reciprocal of the second term, which is 1 minus half z hat dot r hat over r delta L. If I take the reciprocal of that, I get that. Isn't it correct? Because I also make use of 1 plus x due to the 1 minus x. If I take the reciprocal of this, I also make use of this fact. This equals that. If I take the reciprocal of this, I have that. Did I get that right? So I get an r squared there, right?
I know we got the square.
What is that?
Final square, I calculated.
So this half, and then when I subtract the 2, the half becomes a 1, right? Because I move it half delta L over 2 up delta L over. So this delta L is my L. This delta L is my L in this picture. I should have called this delta L. Then everything becomes fine. So what is Q times delta L? Q times delta L is the dipole moment, right? It's what we call mu. It's the dipole moment. So the dipole field is given by this. And it should be also the same as this one over here. This thing over here. Okay. It should also be epsilon 1, epsilon 2 over epsilon 1 plus 2 epsilon 2 E naught A cubed over R squared. So you can figure out what the dipole moment is, and then I can figure out the fact that this should be a cosine theta here as well. Then I should be able to figure out that Q delta L should be equal to epsilon 1 minus epsilon 2 over epsilon 1 plus 2 epsilon 2 E naught A cubed. Okay, that is what the, if we compare this equation with that equation, I figure out that the dipole moment of the very small particle that has an electric field next to it is given by this formula. Am I right? Did I get everything correct? Okay, so I know the dipole moment of this. But what do you know about a far field due to a Hertzian dipole? We studied Hertzian dipole in an undergraduate course. If we have a Hertzian dipole, we often write the solution as this. And what is the far field due to that Hertzian dipole? We can go through this quadratic function using the machinery. Dot with ZIL. When you put it through the quadratic function, we get this thing. But this is G times J. And J is that thing. And then you can see that this is actually equal to I omega mu IL. And then in the far field, you can approximate this with K hat, because del becomes IK. So this should be minus del over K becomes IK hat. So you have this thing over here. And then you have to dot this with Z. Okay, dot with Z somewhere, and then you have that. So this is a far field due to a Hertzian dipole. And what is I minus K hat, K hat? how would you simplify that in the far field?
Theta hat plus theta.
Very good. Okay, we learned that any identity operator can be just written. We learned this formula before, right? Something like this: Fn, Fn. Given any complete autonomous set, you can form an identity operator very easily this way. And we know what is a complete autonomous set in the cylindrical coordinate. Theta plus phi hat plus r hat must be equal to I, the identity operator in the 3 space spanned by these 3 autonomous vectors. And hence if you expand that in terms of that, and k hat is just r hat, they point in the same direction. And then when these two subtract each other, you only have theta hat, and then phi hat. So the far field due to a Hertzian dipole can be easily written down and then you will have the fact that the far field, okay, is I omega mu I L, and then theta hat dot c plus phi hat dot c e to the I k r over 4 pi r. Yeah, that's the thing. But what is phi hat dot z hat? If you visualize this in your mind, phi hat dot z hat.
0.
Always 0, right? If you look at z and then z and theta and all those things. Second term is 0. What is theta hat dot z hat? What is that?
Cosine theta.
Cosine theta, right? Cosine theta. So this is equal to I omega mu I L cosine theta, pointing in the theta hat direction e to the I k r over 4 pi r. This is the far field due to a dipole. So if this dipole radiates in this manner, it would radiate and become a field like that in the far field. But what is IL? I is dq dt, is I omega q. IL, the length of the dipole, the antenna, is I omega ql. So it's actually equal to I omega p, dipole moment, or mu. Actually we call mu in the quantum, in the nano optics book, we call it mu. So QL is the same as Q delta L here. And then we can match up the two. Okay? We know what Q delta L is this dipole moment. We just match it up actually. And then you can plug this in to get the far field. You replace QL here with the QL from here. I call it Q delta L, but it's the same. Okay, in this picture, delta L is my same as my L. And then you can get the far field. You can get the far field, and you can get a salient feature about this radiated far field. This radiated far field, how does it scale with frequency? Is it linearly proportional to omega, or is it proportional to omega squared? Omega squared, right? Because I itself is proportional to omega. So one often quoted physics of far field radiation is that this is omega squared times q if you work this out. Okay? Or omega squared times q out. And some other things. Why is it proportional to omega squared? Why is the radiated field due to a dipole proportional to omega squared? You might be asked this question in your qualifying exam. It's a very fundamental physics of electromagnetics. But you may not have learned it in your previous courses, but let me just tell you what the reason is. The reason is because radiation of a particle is proportional to, radiation of a charged particle is proportional to its acceleration. So if you imagine this particle moving back and forth, the reason why a dipole radiates is because it's accelerating the charges between the two poles, okay? And that acceleration is proportional to omega squared. If you take up a physics book like Jackson, he will tell you that radiation is proportional to the acceleration of a charged particle. And that is the reason why it's proportional to omega squared. So there's a fundamental reason for it. Okay, and this you can see from Rayleigh scattering. And so because the E field is proportional to omega squared, then the power, yes?
Where do you have the acceleration?
Acceleration is the, if I call this x, right, if I think of the charge moving back and forth, it must move back and forth in a time harmonic fashion. So it must have been accelerated back and forth. So if the charge is moving back and forth, say this is the z coordinate. The charge must be moving in this fashion. And if z is time harmonic, then this is proportional to omega squared. Right? It's where the acceleration comes from. If you assume that these charges are in time harmonic motion. So they are going about the omega squared. And that's one thing that you should know. Another thing is that because the energy, when the electric field is going as omega squared, the power density, which is in the far field, can be approximated like this. Has to be proportional to omega 4. Okay, omega 4. The power scattering. So what you see is that if you look at the scattering cross section of a small particle, okay, if you look at the scattering cross section of a small particle, you will find that it's actually proportional to omega 4. The scattering cross section is usually denoted by sigma, and it has omega 4 power. And this is due to small particle scattering. The higher the frequency, the more the scattering, the larger the cross section of this particle. It means the higher the frequency, the larger the load. That's what cross section means. Cross section means the size measured in terms of an area. Okay? And you can read up about the meaning of cross sections in many electromagnetic textbooks. So this is also something that explains why the sky is blue. So how can you use this curve to explain why the sky is blue?
So the wavelength is very short compared with the other.
Right, the blue light gets scattered more than the low frequency light. So if the sunlight comes and it comes through the atmosphere, it's the water molecule or the air molecule that is producing the scattered sunlight. And the blue light gets scattered more. So you're not looking at the sunlight directly, you're looking at the sunlight through atmospheric scattering. And the blue light gets scattered more. That's why the sky looks blue. Yes?
Why the sunset is red?
Oh, the sunset is red. Does anybody know why the sunset is red? Yes, Kurt?
Aren't you going through like, you're coming through like a direct line of
Okay,
light scattering?
very good. Because the sunset is red because you're looking at the light directly. If you are over on Earth's surface, if there's an atmosphere out there, it's actually very thin. If you think about how thin it is, it's amazingly thin. Okay, this picture is a distortion of the Earth's atmosphere. So if you're sitting over here, looking at the sunset, the sun is over here. The sun is actually much bigger than Earth, though. Okay? So if you look at the sunset, it goes through a thick atmosphere. And the light has to be scattered a lot. So the white light gets scattered a lot, the blue light gets scattered away, and what reaches your eye is the leftover. That's why it looks gray. Because the longer frequency light reaches you, and that is the color of the sunset. Actually, the Earth's atmosphere is amazingly thin. What is the radius of the Earth in miles? 4,000. 4,000 miles, right? Am I right? Is it? 4,000 miles, right? 4,000 miles radius. Am I right? I remember to go around the Earth once is about 23,000 miles.
4,000 miles.
So you divide by 6, roughly 4,000 miles, right? 2 pi is roughly 6. So if you go around the Earth once, it's 23,000 miles. So if you divide by 2 pi, it is about 4,000 miles. So this is 4,000 miles. Okay? But how tall is the Himalaya mountain? Mount Everest?
8848.
What?
8848.
What do you say again?
8,848 meters.
8,000. What is this in miles? I can't do metric very well. I live in this country for too long. 1.6, right? About 5 miles, maybe. So if you look at this, Mount Everest is somewhere up there, and this is just 5 miles compared to 4,000 miles. So it's a small blip on the surface of the Earth. And then if you go up onto Mount Everest, you have to wear oxygen tank. No more air out there. Okay, the air becomes very thin. So the atmosphere is actually very, very thin. Much thinner than your orange peel. If you peel an orange, look at the thickness of the orange peel, then it's much thicker than the ratio of the atmosphere to the Earth size. Okay, so it's amazing that we live in that very thin atmosphere. Very, very thin. And this is how you do Rayleigh scattering, and this is some of the salient features that you need to know about the Rayleigh scattering. And then of course, as you go to frequency, it does not go up indefinitely, it has to come down.